Right, so hello everyone, happy Monday. Today is July 11th. We are continuing on with slide 35. Then we'll go on to the homework. So I'll go ahead and share my screen. We left off about talking about, how to form epoxides. We left off how to break them. Here's the previous slide, slide 34. We can form the epoxide, through a couple different ways. We haven't talked about breaking them, but if you use a strong nucleophile, you can go ahead and break that epoxide apart because it is pretty strained with a 3-ring. Your 3-ring is going to be has the most strain, so it's going to be easily breakable by by a nucleophile. They're talking about a couple different ways and saying, the epoxidation methods we've discussed so far are not enantioselective, so you're going to get the R and the S. So epoxidation of an achiral alkene produces a racemic mixture, and that's what they're talking about here. So what they're going to talk about is, you get this racemic mixture, and how can we get away with this? And they're going to go into this sharpless catalyst as a way to, not to have a racemic mixture. But to get to there, they said the epoxidation forms a racemic mixture because the alkene can react in either phase. You can see this right here where that epoxide can, here it's forming on the top, here it's forming on the bottom. So to selectively react with one phase of the alkene, a chiral catalyst would have to be used. No, that's because it can form above the plane or below the plane. So the sharpless catalyst is a chiral complex of titanium tetraisoperoxide and diethyl tartrate. This catalyst will cause an enantioselective epoxidation of allylic alcohol, and that's because you're going to either pick the positive or you're going to pick the negative one. So a given enantiomer of the catalyst DET will favor the formation of given enantiomer of the epoxide. So if we pick the positive one, we're going to form the enantiomer above the plane. If we pick the negative one, we're going to pick form the epoxide below the plane. So it's enantioselective. And it's pretty good because it says it gives us 98% yield for that process. And it shows right here. This is epoxides are useful as synthetic intermediates because of their significant ring strain. Epoxides are reactive towards a weak and strong nucleophile, such as Grignard reagents, hydride reagents, alcohols, and alkoxides. So stronger nucleophiles react readily with epoxides. There's a lot of strain on there, so this is going to be a favorable reaction. So it says in the first step, the hydroxide functions as a nucleophile and it opens the ring in an SN2 process. Then there's a proton transfer. The opening of the ring is thermodynamically favored due to the relief of the ring strain. Because although epoxides are typically not good leaving groups, the ring opening is thermodynamically favored, and they show that right here. Epoxides can be opened by many other strong nucleophiles, and they give you a list of some nucleophiles that have the ability to open up that epoxide. So you have your Grignard reagent right here. You have your thiol group here, cyanyl group, lithium, aluminum hydride. So a hydride could open it up. So there's many different possibilities. So regioselectivity on the epoxide ring opening is an SN2, and so the least hindered carbon is more reactive towards a strong nucleophile. You can see that right here. So this position is less hindered, so the nucleophile attacks here. You can only imagine this having some hindrance right here, therefore it's not going to go there. It's going to preferably go there. There's less stuff that gets in its way. It says, as with an SN2 inversion, if configuration is also observed. You can see that the configuration has been inverted. However, where it's released at, it maintains its configuration right here. And you can see that here, but there is an inversion on this side. So acidic conditions can also be used to open epoxides with a weak nucleophile. So we have a proton transfer, and then we have the SN2 followed by the SN2 reaction. It says water or an alcohol can be used as a nucleophile under acidic conditions. Antifreeze, ethylene glycol is made industrially by this method. So we take ethylene oxide plus H2SO4 with water, and we get ethylene glycol. So we have a proton transferred followed by an SN2 reaction. And then another proton transfer to deprotonate that water molecule that just formed. So this is how you form ethylene glycol. So under acidic conditions, the nucleophile still attacks at the less substituted carbon if a primary and a secondary carbon are present. But things change but if a tertiary carbon is present, then the nucleophile will attack at the tertiary position. And the reason being for the tertiary, it will be on the next slide. The reason for the tertiary position where the attack occurs is because since the epoxide is cationic under acidic conditions, electronic effects result in the carbonyl bond, CO bond to a carbon oxygen bond to a tertiary carbon to be much weaker. So this is going to be stronger here. This is going to be weaker. So it's going to preferentially attack here then. So here for the primary and the secondary, so the attack is based off of sterics. And for the tertiary attack, that's the dominant factor is going to be based on electronic. It says, but under acidic conditions, inversion of configuration is still observed regardless of which carbon of the epoxide is attacked. So these are some key concepts with the epoxides. You can see that really nicely right here. If the attack took place right here, that methyl group shifts up, and you can see that up right here. So the configuration has been inverted. So the sulfur appears. Let me get some water. The sulfur appears just under the oxygen on the periodic table. If you look at a periodic table, you'll see that sulfur is just below oxygen. The thiol group, the sulfur is the analog of an alcohol. So the name of a compound with an SH group ends in thiol rather than OL. So here we have 3-methyl-1-butanol. On the right-hand side, we have 3-methyl-1-butane thiol. It says thiols are also called mercaptans. And the mercaptan name, that's just a traditional name that's been kept. So the mercapto prefix is used to name the SH as a substituent. So 3-mercapto 3-methyl 1-butanol. It says dimercaprol is used to treat mercury poisoning. So if you ever poisoned by mercury, this is what this could be a compound that they could potentially use. Sulfur binds to mercury. There's also a couple amino acids with sulfur on them, methionine and cysteine. And sometimes you can find mercury in people's hair due to the sulfur kind of preferentially binds to mercury, and that's a good place to find or go looking for mercury then. And it's because of the sulfur bonds. It says thiols are known for their unpleasant odor. Skunks use thiols as a defense mechanism. If you ever have an animal sprayed by a skunk, you want some baking soda, hydrogen peroxide, Dawn dish detergent, and there's a certain way you mix that up. There's certain proportions, and then that should really help out. The chemists that developed that mixture, one of them's to attack the oil, because that skunk oil is pretty oily, so that's why you have the Dawn dish soap. And then you have other things like the peroxide to help, it forms radicals, can help break organic compounds down, and the baking soda is used in there too. Methane thiol is added to natural gas methane so that gas leaks can be detected. If you smell gas, the reason why you smell it is because of the methane thiol, otherwise it would be odorless. The hydrosulfide ion is a strong nucleophile and a weak base, and HS promotes SN2 rather than E2. So we see an example of an SN2 reaction right here. We're just replacing that bromine with the SH group. And they're showing you how to make a primary thiol, and on the bottom reaction, that's a formation of a secondary thiol. So it says thiols are oxidized to disulfides with bromine under basic conditions. So we have this disulfide group, and they show you the formation of the disulfide below. So that sulfur attacks that bromine by SN2. Then there's another SN2 reaction with another SR group, and then bromine's a good leaving group. And now we have that disulfide bond right here. So we have the thiolate attacks the bromine, the Br2, and then another thiolate, does another SN2 reaction, and bromine is good leaving group. So we have our disulfide. So to make the skunk mixture, I don't know if you're ever interested in this, but you take 1 quart of 3% H2O2, you take a 1/4 cup of baking soda, and you'd have 1 teaspoon of liquid dishwashing soap, and I use Dawn, to be honest with you. I've had this happen before, so I keep this stuff on hand. When you have dogs and you live out in the country, you know, it's really unfortunate when that happens. So disulfide can be reduced to corresponding thiols with zinc metal. The linear conversion between a thiol and a disulfide can also occur directly via free radical mechanism. So the bond dissociation energy of SS bond is only about 53 kcal per mole, and so the bond is easily made and broken. The shape of proteins relies on this bond being easily broken and made. All right. Sulfur analogs of ethers are called sulfides or thioethers. So here, you know, you see diethyl ether on the right or left, and then you see diethyl sulfide on the right. Sulfides can also be named as a substituent. So we have our methyl thiol group on the right-hand side. So it's a 1,1-dichloro 4-methyl-thiol cyclohexane. So at the 1 position, you have 2 chlorines, right? That's why they have 1,1-dichloro. And then at the 4 position, you have your methyl thiol group. And it's a cyclohexane. So that's how you go about naming that. All right. Sulfides are generally prepared by nucleophilic attack of a thiolate on an alkyl halide. And recall that thiolates are formed by deprotonated thiol with sodium hydroxide. So sulfides undergo a number of different reactions. Here they're showing you an SN2 substitution with an alkyl halide. The product is a strong alkylating reagent that can add an alkyl group to a variety of nucleophiles. Here we're seeing it's adding that methyl group to this nucleophile right here. All right, so sulfides can also be oxidized as sulfoxides or sulfones. So here we have a sulfide oxidized to a sulfoxide and then a sulfone. The choice of the oxidizing agent depends on whether one needs to make a sulfoxide or a sulfone. So sodium metaperoiodate can be used to form the sulfoxide, and hydrogen peroxide can be used to form a sulfone. So there's your two different methods to form a sulfoxide or a sulfone. There's other ones out there too, but they show you two right here. Yes, so bond has very little double bond character. The 2p orbital on the oxygen poorly overlaps with the larger 3p orbital on the sulfur. So we have significant resonance contributions. To get this one over here, all you move is these electrons here, get this one. For this one, you move them here, move them here, you get this one. And why is it negative? Because if you 6 minus 7 equals minus 1, and you have 6 minus 4, and that's how you get plus 2. It's 0 overall, because if you add minus 1 plus 2 plus a minus 1, you get 0. Because sulfides are readily oxidized, they make good reducing agents. DMS is used to reduce the ozonide and complete an ozonolysis reaction. I've shown you. Okay, we have this right here. We add this, we get these two compounds, and we get this. So epoxides allow for installing two functional groups on adjacent carbons. Whenever you see two adjacent functional groups, you should think of an epoxide made from an alkene as a starting material. And I kind of show it to you right here. You can make this epoxide here, then you can add these two other groups right here. So by reacting an epoxide with a Grignard reagent, the carbon skeleton can be modified. So, depending on what your Grignard reagent includes, you can modify, the compound, the molecule. Think of the alkyl halide as a starting group or starting material to which carbons will be added via the Grignard reagent. The epoxide consists of the carbon chain that will be added to the alkyl halide. And what you're going to do right here, once you have your Grignard reagent, you can come attack, this will be released, and that's how you get this product here. So an epoxide yields a longer carbon chain with a functional group on the second carbon of the newly installed chain. A carbonyl would be used to install a functional group on the first carbon of the newly installed part of the chain. So they're showing you a couple different ways to do this. So the two carbonyls were introduced from the epoxide, because you can think about the epoxide. Let me draw this right here. So you can add these two carbons. It says, consider the reagent necessary to accomplish this synthesis below. So you get over here, we think we're talking about epoxide, so you're going to probably have an epoxide. And you'll probably want to use some type of Grignard reagent. So we can insert that. Now we have this ring opening here. This will be released. But then we're missing this right here, right? This is missing here. So we'll just add this right here, and we have our compounds, and then there'll be some type of protonation. And I just show that right here. All right, so let's come back at 10:50. We'll go on with the homework. So I'll see you then. All right, so welcome back, everyone. We're going to go on with the homework, but before we do the homework, just wanted to show you some students are asking where the due dates are at. I just want to show this real quick. Please note that, nothing will be due before we do it in class. So we'll always have the opportunity to do it in class, and then it'll always be due afterwards. So let me bring this up. I'm going to share my screen. So if you go on the Achieve website, you're going to see, okay, chapter 12 was due on July 9th. Chapter 13 is due tomorrow. And we should have chapter 13 homework due tomorrow. If we don't, we'll push the due date till Wednesday. But if you're listening asynchronously, please note, be on top of the homework, watch the lectures. I know most of you are asynchronous, as we have 47 students in the class, and we only have 11 students with us right now. So most of you are asynchronous. So just please keep that in mind that, if you are listening asynchronous, you are still responsible, for the homework when it's due. Another thing I did was I posted, I sent out an email yesterday evening regarding the lab reports. I just want to see them myself to see where you are in the lab. It's not required, but it just gives me a kind of an idea of what's going on. Please still send your lab reports to, your laboratory teaching instructor, because I have, I'm not going to be grading them. That's a separate class. So I just really want to see, kind of what you guys are doing. All right, so those are my announcements. We'll do a new share. So if you are listening asynchronous, it is your responsibility to get this homework done. So write the common and systematic names of the ether that has the given structure. So we have this structure right here. I'm not going to draw all the hydrogens, but we have something like that. So the common name will be ethyl methyl ether. So we have ethyl methyl, because E comes with 4M, right? Ethyl methyl. Just going to make sure I'm spelling that right. Ethyl methyl ether. And the systematic name is methoxyethane. So we have question 1 done. The next question is kind of similar. It shows us a structure. It wants the common name. The common name is, we have a phenyl group, so it'll be methyl phenyl ether. So we have methyl phenyl ether. Question 2. Question 3 says select the common name for the ether. Again, something similar. You see you have 2 cyclohexyl groups, so it's going to be dicyclohexyl ether. So 3 is dicyclohexyl, because you have two 6-membered rings, that are separated with an ether group. An ether group is your ROR. So we have question 1 through 3 done. There's a lot of naming right at first with this homework. So this one is methoxybenzene. If your homework problem doesn't show, just reload the homework. It may happen on the test, so make sure you're able to reload the homework. Last semester there was some technical difficulties, but if the student just restarted the exam, it was fine. That's why I give you 3 hours instead of just an hour and a half. That way, if anything comes up, you're able to take care of it. Okay, let's see. What does question 4 have in store? Oh, this looks like a crown ether. So it says draw the structure of 18 crown 6. So what does the 6 mean? Let's we could even do it on here, this slide. The 6 means we have 6 oxygens, and the 18 means we have 18. So that would be a total of 18 carbons and oxygen. So you'll have 12 carbons plus 6 oxygens. That's how you get 18. Oh, this is a lot. It just looks like this, and you have to do it, I'm not the best drawer of things, so. If I don't line it completely up, it's okay. Or something like, so 1, 2, 3, 4, 5. I have 6, and you should count 18, elements around there, so that should be good to go. see something.
I just wanted to let you know you're muted, so we can't hear you.
Hey, sorry about that. Sorry about that. So, did everyone understand what I was doing on question 6? So question 6 just wants us to push arrows. The first two, I just kind of left a lot of it blank. That's only because it already has it pre-drawn for you. So I just was showing the electron movement. And the third step, it does want the intermediate. So I did draw out the structure then. We have the sulfur too. So that's all looking good there. It says modify the structures and draw the final product. So step 4, we'll draw the final product. So I'll kind of keep it like this. So we have Got that one. We got the sulfur group up here. This sulfur group's the same thing, so I'm just going to drop it down. You're going to add that to here too. So you're going to add that one. And then we form the ether. So you have all that going on. All right, so that should be for question 6. We'll go on to question 7 then. So question 7, it says draw the neutral organic product. So we'll go ahead and do that. So this tert butyl group. And it's going to have an ether on it. So this will be the product that you draw. And you get this because you have this right here. And this double bond is going to extract a proton. If it does that, then you're going to have a tertiary carbocation right there. This will be tertiary. Oh. Then you have this coming in here like this. You can kind of see where this is going then. And then you're going to deprotonate that. You're going to deprotonate this right here. This will be gone and you'll be left with this. So I'm going to draw this as the answer that they're looking for. All right, any questions on this one? All right. What is it? We're gonna go on to question 8 then. Question 8. So it wants us to come up with the final product. So we have a phenyl group. I might not draw the phenyl group all the time. I'm just gonna abbreviate. That's my shorthand for it. But we have this going on right here with the mercury. So we have this. So when this pushes up right here, I'm talking about this one, then it's going to be released. Okay. We have this. Then we can have, then we're going to have a ring opening. So when the methanol attacks, it's going to do it at the more substituted carbon. So the more substituted carbon is right here. And we have a methanol attacking it. Oh, let's draw that better. We're going to have a ring opening. So once we have that ring opening, we're going to have loss of a proton. And where we can get the loss of a proton? Well, we still have this floating around, right? So we have this right here. And one of these floating around, let's have a negative charge. It's going to want to take that. It's going to put this right here. So to get rid of this mercury group, we're going to have a hydride come in. It's going to come in right here, and this is going to be released. So then we're going to get our final product. I'll draw the benzene ring for the final product because they're going to need it. Here's that methyl group right here. I'll call it X. And you can see that X, this will be X. And then you'll have your, this group right here. All right, so that should be it for 8. So 9, it says show the alkyl bromide and alcohol used to make methyl T-butyl, either using the Williamson ether synthesis to the right of the retrosynthetic arrow. So, what they show us is this, like some chicken feet or turkey feet. But to get this, all you need is the alcohol right here, and you can imagine this going through an SN2 reaction. Now with the bromine as a good leaving group, but I don't want to show all that because it doesn't want all that. It just wants this right here. So you're gonna put this in for the alcohol. You're gonna put this in for the alkyl bromide, and you'll have the right answer. Then let me see something. Then wants a mechanism. So step 1. No, sorry about that. We have the arrows going right there. We'll do step 2. And that bromine is going to be a good release. It's going to be released through an SN2. And step 3 says draw the products. So that will be it for 9. And so go to 10. So kind of like before, it wants us to draw the alkoxide and draw the alkyl bromide to do this reaction. So the alkoxide will be here. Alkoxide. You can just imagine this attacking. I shouldn't draw that arrow in there, but I'll show it what I mean. We can just imagine this going here and then that bromine being a good leaving group, but doesn't want that. And here's the alkyl bromide. So here's your 2 starting materials. All right. We'll go to 11 then. I'm just gonna make sure. I'm just going through these, and it seems like we're going at a pretty good pace. I don't think we are. For some reason, I think. All right, so for 11, it wants us to identify the reagents. So we're going to select for reagent 1. This is 11 for reagent 1. I'm going to select CH3, CO3H. It says identify the step for step 1 product. We're going to form the, this is the S1 product. S1P is what I'll call it. Identify the reagent for 2. Here's the step 2 product, S2P. Then we're going to identify reagent 3. This will be the sodium aluminum hydride. Good source of hydride. And then it says it wants a step 3 product, so we'll call it S3P. So you're going to draw all those. Not draw them, just select them actually. All right, so that was 11. So we'll go on to 12 then. 12, it wants a bunch of different products. So we start with this thing right here. Start with an ether. And then what's going to happen is, this has two pairs of electrons. It'll protonate itself. This will become a good leaving group. Once it becomes a good leaving group, you have this iodide sitting around. What do you think it wants to do? Well, it wants to go on the attack, and then this will be gone. So your first product will be product A. So we have that. So then, product B, well, we know what product B will be. We'll just have the alcohol. So product B will be the alcohol. And let's see. And then it wants a further reaction. Let me think about that. Oh, well, it's basically going to be the same thing again. So we're going to take this, and this is going to pronate itself. This is going to be gone. Then, you're going to have this right here, and you can just imagine this being a good leaving group. This comes in right here, and we'll get product C.
What?
Nothing.
What?
All right, so we'll go to question 13. So it says add curved arrows. So that's step 1. That's step 2. And this will be released to here then. Step 3. And step 4. All right, so let's go to 14. 14 says, predict the oxidation product of treating the given alkene with the reagent shown. Include stereochemistry where applicable. Include hydrogens on chirality centers. It says, note that MCPBA is metachloroperioxybenzoic acid. What's gonna happen is it's gonna add this like that. So it forms the epoxide or oxyurane. I'm going to put 15 on the same slide. There's not much to 15. 15 has this epoxide, and then it has a Grignard reagent. So you can just imagine, remember this is it'll go to the least substituted side on this one. Since this is a primary versus a tertiary or a secondary. So this is another carbon, so it'll come here. That'll be a ring opening. And then it's going to pronate itself. And we'll have this. Oh, let me redraw that. All right, so let's go to 16. 16, this will be our last question for today. We're just going to be pushing arrows here. Push them here. This is step 1. Step 2. And finally, step 3 is just the final products. That's it. So that's it for today. I'm gonna stop recording. If you have any questions, please feel free to stay behind and I'll go ahead and answer those.